Hello, everyone. Could you see my screen?
Yep.
All right. Hello, everyone. My name is Khang, and I'm an undergrad computer science student at Washington State University. Today, I'll be sharing the work I've done during my internship with Agite, focusing on two systems we developed for smart orchard monitoring. One that monitors the environment for frost risk, and another that analyzes fruit health using vision and thermal sensing. A little bit about me. I've had the opportunity to work with mentors Dr. Lavcoat and Kesha Dadalai. My interests lie in software engineering and machine learning, especially how they can be applied to real-world challenges like agriculture. And this internship allowed me to explore both of them on a deeper level. The two projects I worked on is Weather Sonde and Orchard Fruit Analysis System. These two projects complement each other as Weather Sonde focuses on environmental sensing, detecting temperature inversions to help prevent frost damage. On the other hand, Orchard Fruit Analysis System handles fruit level monitoring by analyzing thermal and color data to assess fruit health. Together, they support decision making in Orchard. So let's dive into the first project, Weather Song. For this project, I was provided with a rebuilt sensing device, and my role was to develop a mobile application that could communicate with it, visualize data, and assist growers in the field. And the problem that we're addressing is frost damage in early spring, which can severely damage buds, flowers, or even entire trees. One major cause of frost events is a phenomenon called inversion, or temperature inversion. Normally, warm air stays near the ground while cooler air sits above. But during calm, clear nights, this flips. Cold air sinks to the ground, as you can see in the second picture, and warmer air floats above it. This creates the ideal condition for frost. The challenge is that growers can't really see or measure inversion directly, and that's where the WeatherSound system comes in. The WeatherSound device is a lightweight drone-mounted sensor package that detects inversion events by collecting vertical and horizontal profiles of temperature. The goal is to give growers real-time data to decide when and where to activate frost protection tools like wind machines. This is an outline of the WeatherSound system architecture. As you could see right here, it is the ESP32 microcontroller as the main processor. We use LiPo battery to charge the controller. It takes up to 30 minutes of charging and work up to 4 to 5 hours of usage. And for environmental sensing, we have a sensor that sense our real-time location, a sensor that detect temperature and humidity, and a sensor that detect pressure and altitude. We also have a radio telemetry attached to the device so that it could communicate with a mobile device on the ground, which also is connected to another radio telemetry using the USB. Here you can see the weather sound device. From left to right, we have the radio telemetry that is connected to the phone, the mobile device. And the second one is the weather sound device itself. And the last picture is the weather sound device mounted on the drone. Here's a quick demo of the mobile app that I built to communicate with the weather sound device. I built with React Native. So here on the first page, you could see a map that shows the drone real-time location along with some temperature information. On the second page, we could see real-time data coming in along with like inversion data, which we focus on. On the historical tab, we could see those data being those historical data being stored in our database and being shown right here. On the analytics page, we could see a graph of temperature and altitude. We could switch to the graph of humidity and altitude. On the weather page, we could see real-time weather data. And lastly, on the setting page, we could change our global temperature and distance unit. We could also go to the knowledge center to learn more about inversion details. To test the device, test the mobile application, and collect data, we conducted a flight at the Pullman weather station because this location gave us reliable ground truth to validate our data. Census reading were collected in real time, and the mobile app locked everything into a local SQLite database for further analysis. Here is one of the graphs that I've conducted from our data collected from the field. Um, as you can see, the inversion intensity increases with altitude, which aligns with our expectation, um, that indicating that inversion is present and that our device could detect it. Moving on to project two, we shift the focus from environment to the health of the fruit itself. And we aim to address manual monitoring and fruit health challenges. So traditionally, orchard monitoring is done manually, which is labor intensive and time consuming and often subjective. But more importantly, many types of uh, abiotic stress like sunburn, dehydration, or heat stress don't show up visibly until the damage is already done. And at that point, it's already late. And that's the problem we aim to mitigate with our orchard fruit analysis system, a solution designed to detect stress indicators early and automatically using vision and thermal sensing technology. So our orchard fruit analysis system is designed for automated real-time fruit monitoring, specifically targeting apples in our deployment. It uses RGB and thermal imaging to detect fruits and analyze their coloration and surface temperature, which are key indicators of early signs of sunburn stress and so. The data collected by the system can help support better decision making in the field, like adjusting irrigation, harvest timing, or deploying shade nets. It also serves as a foundation for the sunburn detection algorithm developed by another engineer of AgWeatherNet. And finally, the system is LoRa compatible, which allows us to wirelessly transmit process data over long distances. And here you can see a very simple system flow of the system. Uh, so the oak thermal camera took two photos of the apple simultaneously, one RGB picture and one thermal picture. It then sent those pictures to our edge computing device, which does all the image processing and give us all the outcome that we want, like fruit surface temperature and temperature ranges, like minimum, maximum, and average temperature. It then are transmitted via LoRaWAN to a LoRa gateway and forward the information to a backend server for storage and visualization. And this slides, you can see the technology stacks that we use for our hardware. We use Raspberry Pi 5 for image processing, with Pi 4 for powering the Raspberry 5 and schedule it to run periodically. The Def AI camera to take photos of the apple. For the software, we use YOLO and PyTorch for machine learning, OpenCV for image processing, and a web interface with Flash purely for troubleshooting. And here you could see our software interface. On the first picture right here, you could see the RGB picture of the two detected apple. We then use a masking technique in the picture below it to find the region of interest. As you could see, the two white holes indicating apples. We then align it to the thermal picture to detect the apple in the thermal image. And with this, we could calculate the outcomes that we want, like temperature ranges, as well as fruit surface temperature. And this is the web interface that we built with Flash purely for troubleshooting. As you could see, we could select each individual detected apple, and we could also see the color analysis results as well as the thermal and FSD analysis results. Here you could see the orchard fruit analysis system in action as we deploy it in the orchard. So you could see we mounted our edge computing device on a solid system so that it's powered by the sun. And then we mount the whole device on a pole with the camera um, directly angled at the orchard so that it could detect apples from the canopy and do all the image processing, data processing. Over the course of this internship, I have gained a lot of experience and knowledge. Firstly, I gained a deeper understanding of agriculture, things like temperature inversions, frost damage, sunburn stress, and how these factors affect orchard health and fruit quality. On the software side, I worked across the full stack from backend and mobile development to database design and migration. I also got hands-on with the WeatherSong, building mobile interfaces, handling data migration, and learning how to wrap machine learning models into practical Python pipelines. Even though I did not train the model myself, but I did get a chance to work around them, integrating the pre-trained models, integrating algorithm for FSD or fruit surface temperature analysis, and stitching together various software components. Hardware-wise, I became much more comfortable with the Raspberry Pi and the Linux operating system. I spent a lot of time configuring devices, writing scripts, making scheduler in WidiPi, and debugging issues in the field. Speaking of the field, deployment taught me a lot, from dealing with unpredictable weather to solving issues on the fly. I learned how to troubleshoot in real time and adapt quickly under pressure. Finally, I've been working on technical writing and communication. I'm currently helping draft a white paper on the weather science system, which we hope to publish soon. And that concludes my presentation. This project has been an incredible learning experience, blending agriculture, machine learning, hardware, and software in real-world setting. I'm grateful to the Agai Institute for the opportunity. I would like to thank Dr. Lavcoat for his mentorship, Keshraf Dadale for his guidance, and Rizab Goyo for his support and collaboration. Thank you all for listening, and I'm happy to take any questions.